All right, folks, welcome back to video 2. We are going to finish off one variable analysis today. So that should take us through basically the first 3 chapters of the textbook. So in this video, we're going to talk about percentiles and we're going to talk about z-scores, and then we're going to do a bunch of practice problems. All right, so this video should be much shorter than the last one, and it definitely has more practice problems in it. So this is definitely a good one to go back and review. All right. I'm using a new screen recorder, so you shouldn't see like the little zoom box where my camera is supposed to be. You should just be able to see the full screen now a little bit better. And this is how I'm going to make the videos going forward. So we're getting better with each video we make here. So let's start by hopping back in here and talking about percentiles and percentile rank. So before we even look at this text, like, let's just imagine you took a test and I told you you scored at the 90th percentile. Okay, this would mean that your score on that test was greater than or equal to 90% of the class, right? So you'll see there's actually more than one definition for a percentile, right? So your 5 Steps to a 5 book says the percentile rank is equal to the proportion of terms in the distribution less than the term in question. But you're going to see that I like this definition down here where it says some texts define the percentile rank of a term to be the proportion of terms less than or equal to the term. And that's the version of the definition that we're going to go with. So if I said you were at the 90th percentile, that means you scored greater than or equal to 90% of your peers on the same examination. They clean up the language in here too. If you remember during the year, I stressed that when we speak, we say a term is at a percentile, not in a percentile. That's an easy mistake to make, but if you were writing a short answer question that involved percentiles, please use the term at, because it is a location. Okay. And before we quickly transition into z-scores, right, which are also very related to percentiles, we can just quickly review talking about a box plot real fast, because you'll notice in here they talk about the 5-number summary, and they talk about how quartile 1 is the 25th percentile, the median is the 50th percentile, and the third quartile is the 75th percentile, right? And that should make sense, right? Because if the median is the number that splits a data set in half, then the value of the median should be greater than or equal to 50% of the data in a list, or 50% of the data in a data set. Quartile 1, or the first quarter of the data, you got to think of this as a cutoff, right? The first quartile is a location in a distribution, and it's what separates the bottom 25% of the data from the top 75. And likewise, the third quartile is what separates the bottom 75% of a distribution from the top 25%. And a box plot is a really nice way of showing this, right? So let me draw a quick box plot here, and excuse my sloppy drawing. I'm doing the best I can with the mouse, but let's imagine this was a box plot of test scores, right? And I can put a number line down here. I'm not going to put any outliers on this box plot just for the sake of ease here, right? But if we look and I start labeling, this box plot would tell me a lot about the test scores for my class, right? So maybe the lowest score on the test was a 65, and maybe the first quartile is represented by 72, and maybe the median score was an 80. I'm just kind of making these up as we go here. And maybe the third quartile is represented by an 87, and maybe the highest score on the exam was a 96, let's say, right? What's really important for you guys to realize is that there is only 25% of the data set within each of these chunks okay? A big misconception with box plots is that the longer a piece of the box plot is, the more data is inside. And that's not true, right? Box plots are split into 4 equal parts that each contain 25% of the data. The length of any piece of a box plot simply tells you the spread of that quarter of the data, okay? So you can see the lowest 25% of test scores on this box plot were between or equal to 65 to 72. Okay, so that would be a spread of 7 points, right? And then so this is obviously not to scale. I should have made this box in here slightly longer than this whisker, right? Because from the first quartile to the median, the spread was 8 points, right? So 25% of the class got within a 72 to an 80, right? 25% of the class got within a 65 to a 72. Another 25% of the class got between an 80 and an 87. And then the highest 25% of the class got between an 87 and a 96. And these numbers here represent your quartiles. 72 is the score that separates the lowest 25% of the data from the highest 75%. The median of 80 is the score that splits the data set in half, okay? Not by value, but by position, right? 50% of the class got less than an 80, and 50% of the class got more than an 80. And if you're looking at a box plot, just real quick, right? If I draw one more quick box plot here, again, all of these segments contain the same amount of data, okay? This would represent, right, data points from like 26% all the way to 50%, right? This would be your second quartile. The median is the cutoff, or quartile 2 for the top 50%. The edge of this box is the cutoff for quartile 1. So this should represent 25% of the data in the set. But this also represents 25% of the data in the data set. But because they're different lengths, I know that, well, between quartile 1 and quartile 2, there was a greater spread in the data, okay? So from like I said before, 26 to 50%, those students were fairly spread out in terms of their score. But over here, this is again another 25%. I guess I already have that written there, right? But between quartile 2 and quartile 3, the same amount of data is in here. It's just more packed together. Okay, so that's a little bit more on box plots and percentiles, leading us into, okay, z-scores. Because z-scores are another way of describing location in a distribution. Okay, and we're going to practice a lot with z-scores in this video, right? But a z-score basically tells you how many standard deviations above or below average a certain score or a certain term in a distribution is. And you guys should remember this formula from earlier in the year. Try not to worry about the extra notations, but a z-score, or the number of standard deviations I am above or below average, is equal to the score minus the mean for the data set divided by the standard deviation of the data set. So a real quick example, if I gave you guys all a test and the average on the test was a 75, okay, and the standard deviation for the test was 5 points, and you scored an 80 on the exam, intuitively, you guys might be able to understand already that you were 1 standard deviation above average. If a standard deviation was 5 points and you scored 5 points above the average, then you're 1 standard deviation above average. And substituting into this formula, we can see z is equal to 80 minus 75 divided by 5. Okay, 80 minus 75 is 5 divided by 5, and 5 divided by 5 is 1. So in this particular data set, if I had a score of an 80, I'm 5 points above average. A standard deviation happens to be 5 points in this data set, so I am 1 standard deviation above average. Okay, so here is a histogram. All right, it's a histogram because all the boxes are touching. It's numerical data here, right? The fact that there's no bar here above 76 represents the fact that nobody got a 76 on the exam. All right, and oftentimes we're gonna examine data, right, that has this approximately symmetrical shape, right? I could say this thing is probably approximately symmetrical in shape. All right, and this is right when we transitioned into talking about the normal distribution. Okay, so you know, the normal distribution is this roughly symmetric mound-shaped distribution that we've been studying all year, right? And they're telling us down here, this distribution is representing the heights of 100 males whose average height is 70 and whose standard deviation is 3, right? So when I'm drawing these smooth curves and we're working with these smooth curves all year, right? You got to imagine that there's data underneath, right? And we're drawing in the smooth line to kind of make the math a little bit easier for us. And we should also know that if a variable is normally distributed, like something like height might be normally distributed, right? Lots of people are average, and the further I get away from average, you see the less people who hit those heights, right? The further away I get from the average height. But the more people I included in my sample, the closer this picture would start to look to this smooth line, right? You can see that this bar graph doesn't perfectly fit this smooth line, but if I added more data, you would see the bars start to get closer and closer to the way this curve is drawn. Okay, and if I just do some quick erasing here, we can do a quick z-score practice using this graph, right? I'll leave the smooth line in, but they're telling us the average height is 70. So they're saying that this happens to represent the average for this distribution, and the standard deviation is 3. So let's figure out what the z-score would be for one of the people who got this score, right? We don't have a y-axis here, so I'm not sure how many people got a 77. All right, but at least one person got a 77, probably more, right? So if I wanted to figure out this person's z-score, or how many standard deviations above average they were, they earned a 77 on an exam that had an average score of a 70 with a standard deviation of 3 points. So 77 minus 70 is they scored 7 points above the average, and a standard deviation was 3 points. So if we then go ahead and we do 7 points divided by a 3-point standard deviation, we're going to find out that this person was 2.33 continuous if you plug that into a calculator, or you can just know that 3 goes into 7 2 1/3 times, right? So this person was way above average. Okay, they were more than 2 standard deviations above average. All right, but what does that tell us? So we can relate this back to percentiles, right? Here they are drawing in that same smooth curve that I was trying to draw on the last page, right? And you can see again that the bars don't perfectly fit this curve, but that's all right. When we started the year, we used this 68, 95, 99, 7 rule, which is called the empirical rule. And it's an approximation. It says that approximately 68% of data values in a normal distribution will be within 1 standard deviation of the mean. 95% are within 2 standard deviations of the mean, and 99.7. So almost all the data in a normally distributed data set should be within 3 standard deviations of the mean. Okay, And this 95 should kind of be familiar, right? When we are calculating our critical values, when we are doing significance tests, and when we're doing confidence intervals, and we use inverse norm to tell us how many standard deviations should contain the middle 95% of the data, we usually get something like 1.96 and change, right? So that's where the 68, 95, 99, 7 rule, right, is an approximation. Okay, we say roughly 95% of the data is between roughly 2 standard deviations from the average, right? And then that brings us to tying a z-score and a percentile rank together. So if I use a smooth line like this to approximate a data set, and I say it's normally distributed, right? I should be able to figure out what any score in the distribution is in terms of a percentile rank. Okay, so let's do one that's a little more complicated, and we'll use the calculator for the first time. Okay, so here they're going to put z-scores on the bottom this time. So remember, if I'm still working with this set of data here, they told us the average was 70. As a z-score, okay, that would be a z-score of 0. You were 0 standard deviations above or below average if you scored exactly a 70 on the exam. Okay. Now, let's imagine we wanted to figure out the z-score for somebody who was below average on the exam, right? Because this z is to the left, so it's going to be a negative number if it's below 0, right? So let's make up a score right now. Let's say something pretty close to 70, but not quite 70. Let's call it, if you got a 68 on the exam. All right. If you got a 68 on the exam, first we can figure out your z-score, and then we can figure out what percentage of the class you would have done better than at that particular z-score. All right, so let's try that. First, let's figure out the z-score. How many standard deviations below average am I? If I got a 68, well, we're going to use our formula. Score minus mean divided by the standard deviation. Okay, so if I got a 68, I was 2 points below average, and 1 standard deviation was 3 points. So I was not 1 full standard deviation below average. I was 2/3 of a standard deviation below average, or negative 2/3 as a decimal would be 0.666 continuous. Okay, and now for the first time, we're going to pull up our calculator, and we're going to ask the calculator to give us the area of this gray shaded region here that I'm now highlighting in blue. All right, and I can say, all right, if the data is approximately normally distributed, I should be able to figure out what percentage of people scored at or below me. And the way that we do that is with our calculator function, NormalCDF. Okay, so the way that I get to the NormalCDF window is I hit second, distribution, and I scroll down to NormalCDF. We are not ever going to use the NormalPDF button, okay? It doesn't come into play for us. All right, let's come back to our picture for a second, and let's talk about the ways that we could get the calculator to give us our percentile rank, because maybe I forgot to mention, but the area under the curve is going to be equivalent to your percentile rank, okay? So if I'm here in the distribution at this z-score, right, the area underneath the curve to the left of this point is going to be equivalent to the percentage of the distribution that I am larger than or equal to. And there's 2 ways I can ask the calculator to give me this area. First, I can use the actual raw data from the data set. I can use the mean, I can use the exact score I'm given, and I can use the standard deviation they give me for the data set. So in this case, they gave me a standard deviation of 3. So when I pull this up, right, I can say, okay, I want to know how many people or what percentage of people I did better than if I got a 68 on an exam that had an average score of a 70, standard deviation of 3. And notice I'm leaving the lower boundary as negative 1e99. I'm basically, because this is a continuous distribution, I'm trying to give my calculator the smallest number possible to approximate the extreme left side of this curve. So that's where the negative 1e99 comes in. And when I pull this up, okay, I can hit paste, I can hit enter, and here's my percentile rank. If you got a 68 on this exam, you did better than, if I just rounded off to 2 decimals, you did better than roughly 25% of the class. Better than or equal to, I should say, right? But remember, I can get this same number with a z-score. So this z-score really belongs down here, right there, right? If a score of a 70 is 0 standard deviations above or below average, then a score of a 68 is 2/3 of a standard deviation above or below average, okay? And I can talk to the calculator in terms of standard deviations as well. So, and I should get the same number, right? So let me do it again. Second distribution, normal CDF. And now instead of using the raw scores, right, I'm going to speak to the calculator in terms of z-scores, okay? So I'm going to say, all right, my upper boundary is now negative 0.66666. So I was 2/3 of a standard deviation below average. If I look here, back at my curve, that's my upper boundary here, right? I'm not using the raw score 68 anymore. I'm using the z-score in terms of standard deviations. I was 2/3 of a standard deviation below average. All right. The mean in terms of z-scores, remember, right? If you were perfectly average, you're 0 standard deviations away. All right. And now I don't want to talk to the calculator in terms of the number of points, right? Before I was telling it 1 standard deviation is 3 points. But now I just want to tell the calculator, I want them to use 1 as the standard deviation, right? So it's going to calculate the area to the left for me on a distribution that's centered at 0 with a standard deviation of 1 if I am only 2/3 of a standard deviation below average. And you'll see when I paste here, I'm going to get the exact same number, okay? Actually, you can see it's rounded off. It's slightly different, but we had to get out to 1, 2, 3, 4, 5, 6, 7, the 8th decimal place before they rounded this off. And that honestly is just because I only put in 1, 2, 3, 4, 5, 6s, and this is really continuous. So it's really 0.666666666 forever. And if I was able to enter that into the calculator, we should get an exact match between these two numbers. So talking about your position in a distribution in terms of your raw score or in terms of how many standard deviations above or below average you are is the same thing. Okay. So now again, these are z-scores here, right? We could use the calculator to help us find all kinds of different areas under this curve, right? So again, if I have a z-score of negative 0.12 and 0.58, we can forget about what the raw data looks like for a second. I can figure out how much of the area under this curve or what percentage of the normal distribution falls between 1.2 standard deviations below average and 0.5 standard deviations above average. Since I'm speaking in terms of z-scores, when I come to my calculator and I go to normal CDF, right, I want to leave the mean and standard deviation as 0 and 1. Whenever you're talking to the calculator in terms of standard deviations, you're going to leave this in terms of 0 and 1. If you're going to use raw data scores, you can change these numbers to reflect the mean and standard deviation that are given to you about the distribution. So I'm going to change my boundaries here now. My lower boundary is negative 1.2. So let me put that in, negative 1.2. And my upper boundary, I think, was 0.58. And we can find out that in between those two z-scores is about 60% of the distribution, right? So the majority of the distribution is falling between these two scores, okay? And again, we're going to do more practice questions later. But sometimes you might be asked to find the area to the right of a certain z-score, right? So right now they're giving us another z-score of 0.67. So basically 2/3 above average now, okay? If you wanted to find the white space area that I just highlighted in blue, okay? Remember your calculator can actually do this calculation. So you'll notice here, it looks like they're trying to tell you in this diagram, find the area of the gray region, or the area to the left, and then subtract it from 1 to find the area on the other side. And that's valid. You can certainly do that, right? And we can pull up there. So they're telling you to the left of 0.67 standard deviations above average is 0.7486, or about 74.86% of the distribution, right? So to find out the area to the right, they are telling you do 1 minus that, right? So I'll take the 100% and I'll subtract 0.7, whoops, I think it's 7486. And you'll find out that to the right, you should have 0.2514, right? So this should be, this area over here is 0.2514. But I also could use the calculator to give me this region, right? I just have to change my boundaries. I'm going to make my lower boundary 0.67 if I want this blue striped area now. And again, because this is a continuous curve, I want to give my calculator the biggest number possible on the right side here. So that will be, we'll tell the calculator 1E99, just like if we want to use, the left end as the lower boundary, we would do negative 1E99, right? So we can do that real quick. We can go back to second distribution, NormalCDF. And I'm going to make my lower boundary 0.67. I'm going to make my upper boundary 1, and then your E button is right here above the comma. Okay, 99. Since I'm speaking in terms of z-scores, right, I'm going to leave the mean as 0 and the standard deviation is 1. I'm going to hit paste. I'm going to hit enter. And there's your 0.2514, right? Don't worry about all the extra decimals here. Okay, it's the same number, 0.2514, that we got before. Okay, so you can have the calculator give you the area to the left, area to the right when you're using NormalCDF. It just depends on, how you set your boundaries. Okay, and then lastly, so let's go back to this same example where we have a distribution that has a mean of 70 and a standard deviation of 3 points. And what if we wanted to find out what is the score that represents the 90th percentile? I say the 90th percentile because you can see that this X here is drawn in such a way that is splitting the distribution into 90% of the area to the left and 10% of the area to the right. So how could I find this score? This is the opposite function of what we've been doing, right? On this page, or on these slides, I'm using NormalCDF. I'm giving the calculator boundaries, and I'm asking it for me to calculate the area underneath. But here, I might ask, or I might give the calculator an area, and I might ask it to give me the cutoff, okay? So the opposite function, you might remember from class, second distribution, is going to be the inverse norm function, okay? And I can do two things with the inverse norm function. I can, again, speak in terms of standard deviations or z-scores, or I can speak in terms of raw data. So if I pull this up and I say, okay, on a distribution that has a mean of 70 and a standard deviation of 3 points, what score is going to cut the bottom 90% of the distribution away from the top 10, right? And I can figure that out. I'm using inverse norm, and I'm going to give it the area to the left. And I'm going to say on this particular distribution, the mean was 70 and the standard deviation was 3. I can paste that in, and I can see that this is the score that I would have had to get to be in the 90th percentile. I'll round this off at 2 decimals. So a 73.84, right? So I'll pull this back up. X would have to be 73.84. Okay? So that's the inverse norm function. I also could figure out how many standard deviations above average. What would the z-score have to be at this point? I could do the same thing if I hit second distribution and I use inverse norm again, right? Instead of telling the calculator the mean is 70 and the standard deviation is 3, if I wanted to tell me how many standard deviations above average I'd have to be at the 90th percentile of a normal distribution, and I hit paste here, right, I would be about 1.28 standard deviations above average. And if you plug this number here into the z-score formula, we should roughly get 1.28, right? So remember, this 73.84 and change, right? If I subtract the mean of 70 and I divide by a standard deviation of 3, there's that 1.28, right? This score is 1.28-ish standard deviations above average. So it's two ways of describing the same position, right? In terms of your raw points above average, I had a 73.84. But in terms of my standard deviations above average, you're looking at 1.28 standard deviations above average. Okay? So that's the lesson. We did it in 30 minutes, not so bad. And we're going to do some practice questions on the next 3 slides now, and then we'll be done for this video. Okay? So let's read through. You can pause after I'm done reading each question. You can try it on your own, and then you can press resume, and I'll show you how to do it, right? So number 2 here, these are all, again, from your 5 steps from a 5 book. This is still one variable analysis, all right? So it's the first section when they finally start talking about content. It says, Megan wonders how the size of her beagle Herbie compares with other beagles. Herbie is 40.6 centimeters tall. Megan learned on the internet that beagle heights are approximately normally distributed with a mean of 38.5 and a standard deviation of 1.25. What is the percentile rank of Herbie's height? So, I mean, I can draw the diagram here, right? She learns online that beagles have an average height of 38.5. Okay. We find out that the spread of the distribution is about 1.25 centimeters. And Herbie is 40.6 centimeters tall. So he's going to be to the right of 38.5, right? Herbie's got to be over here somewhere. If we want his percentile rank, we need the area to the left of Herbie's 40.6 centimeters. Okay. Again, I could do this in terms of z-scores, or I could use the raw data here. Quickly, let's just do the z-score, right? If Herbie is 40.6 centimeters tall and the average beagle is only 38.5 centimeters tall, and the standard deviation for beagles is 1.25 centimeters, then Herbie should be, and we'll check, 40.6 minus 38.5. 40.6 minus 38.5. So he's 2.1 centimeters above average, divided by 1.25. He's 1.68 standard deviations above average, right? So that's Herbie's z-score, right? I could write that up here, 1.68. And now I can use Herbie's z-score, or I could use the raw data to figure out his percentile rank. Okay, so let's go for it. We're going to use NormalCDF for this, and I'll do it both ways, right? Second distribution, NormalCDF, and let's talk about the distribution of beagles, right? If I pull my picture back up, my upper boundary, if I'm talking about raw scores, is going to be 40.6 I'm going to leave the lower boundary as 1E99. So my upper boundary is 40.6. The mean on this distribution, I want to say, was 38.5. It was 38.5. And they told us the standard deviation was 1.25. And now I find out that Herbie is larger than about 95% of other beagles. So if we come back here, it's got to be answer choice E. Okay, I also could have spoken in terms of standard deviations, though. I could have said, on a normal distribution, if I am 1.68 standard deviations above average, regardless of what the average is, and regardless of what the spread is, on any normal distribution, if you're 1.68 standard deviations above average, you should be bigger than about 95% of the group. So I can tell the calculator that as well. Second distribution, normal CDF. I'm going to leave the lower boundary as 1E99, but now I'm going to speak in terms of standard deviations. So if I'm 1.68 standard deviations above average, the average score has a z-score of 0, and we'll make the standard deviation 1. When I paste, there it is. It's the same exact number. Okay, so I was giving the calculator positions on the distribution. In the beginning, I was speaking to it in terms of the raw scores. I said I'm at 40.6 on a distribution that's centered at 38.5 with a spread of 1.25. And the second time, I said, all right, I'm not going to tell you the raw data, but I'm going to say I'm 1.68 standard deviations above average on a distribution where the average score is a 0, right? 0 standard deviations above or below average with a spread of 1. Okay. So not so bad. That one's not so bad. Let's keep cruising here and look underneath. You can pause too when I'm done reading if you want. It says the mean and standard deviation of a normally distributed data set are 19 and 4 respectively. The value 19 is subtracted from every term in the data set, and then the result is divided by 4. Which of the following best describes the resulting distribution? So think about it, right? The z-score formula, okay, is score minus the mean divided by the standard deviation. And whenever we do this, whenever we convert a distribution to z-scores, we always are talking about the mean score on the standard normal distribution being a 0 and the standard deviation being a 1. Okay, so think about that. If I subtract 19 and divide 4 to every score in the distribution, I'm going to recenter the distribution at 0, and I'm going to change the standard deviation to 1. Okay, you can even just think about a simple list of numbers, right? Let's just think about the data set 2, 4, 6. Okay, the mean here would obviously be 4, and the standard deviation would be 2 because the numbers are 2 apart, right? Imagine if I subtracted the mean from every number in this data set. Okay, so I'm going to make a new data set now. I'm going to subtract 4 from every number in the data set. Okay, 2 minus 4 is -2. 4 minus 4 is 0. And 6 minus 4 is 2. Right? Notice where the distribution is centered now. It's centered at 0. Right? I subtracted the mean from every score in the list. Now the distribution's centered at 0. Right? Then we look, it's easy to see the standard deviation here. Each number is only 2 apart. Right? So the standard deviation, the average distance from the mean has to be 2. Right? This number is 2 away from 4. This number is 2 away from 4. All right? So the standard deviation's got to be 2. Imagine if I divide all these by a standard deviation of 2. Right? Divide this by 2. Divide that by 2. Let's look at the new spread. -2 divided by 2 is -1. 0 divided by 2 is still 0. 2 divided by 2 is 1. And look, now the numbers are only 1 apart, right? So when I subtracted the mean from every score in the list, we recentered the distribution at 0. And when I divided every score in the list by the standard deviation, which we said was 2, just because there's only 3 numbers in the list, and they're each 2 apart, right? Then the standard deviation changed. Look at the spread of these numbers now. They're not 2 apart anymore. They're only 1 apart. -1 to 0 is 1, and 0 to 1 is 1, right? So it has to be A, okay? Let's keep cruising here and try and cut this off short of an hour here. So this one says the 5-number summary for a 1 variable data set is 5, 18, 20, 40, and 75. If you wanted to construct a box and whisker plot for the data set, what would be the maximum possible length of the right side whisker? Okay, so they're telling us that this is the 5-number summary, right? So we got to think for a second. Potentially, we want to just double check that this is not an outlier, okay, before we go any further, right? Before we draw the box plot, we need to make sure that, so first of all, let's draw a box and whisker plot, right? Here's a box and whisker plot, and they want to know the maximum length of the right side whisker, right? Well, if 75 is an outlier, then this whisker is not all going to go all the way out to 75. If 75 is not an outlier, right, then the minimum number is 5, 18. It looks like the median is 20. So I did not draw this again to scale. This actually, let me try and draw it to scale. Let's try and do a better job there, right? This box plot would look like this. Much bigger on this side, right? So this is what we got to figure out, right? The minimum was 5. The first quartile is represented by 18. Then the median is 20. That's really close to 18. And then the third quartile is 40. That's pretty far away from 20. And then this could be a 75 out here, right? So the right whisker could be about 35 units apart, unless 75 is an outlier. So let's check our outlier formula, okay? We're going to say for outliers on the high side, it's quartile 3 plus 1.5 times the IQR. And anything bigger than this cutoff point is going to be considered an outlier. So if 75 is bigger than this cutoff point, then 75 is going to be an outlier, and that's not where the whisker is going to go. All right, so the third quartile is represented by 40 plus 1.5. What's the IQR here, right? 40 and 18 is quartile 1. 40 minus 18 is 22. So 1.5 times 22. And we'll just plug that right into our calculator, right? So this is the cutoff. 40 plus 1.5 times 22. This is going to give me the cutoff for an outlier on the high side. And it's 73. Okay, so look, the right side whisker can't go all the way out to 75 because 75 is an outlier, right? This is the 5-number summary. They're giving you the maximum value. That doesn't mean it's the end of the whisker. 75 is the highest number in the data set, but it's an outlier. The cutoff for the outlier is 73, okay? So that means this whisker can't go out to 75. It can only go out to 73. Okay, anything after 73 is an outlier. Here's 73, and then 75 would be out here as a star, right? 75 is the outlier. So now I know the maximum length of the whisker is got to be 73 minus 40. Anything above 73 is now an outlier. So the maximum length of that right whisker is going to be 73, right? This is basically 1.5 times the size of this box, right? That's as long as this whisker can be. Okay, so 33 units, all right? And we'll keep cruising here. I'm going to try and keep this to under an hour, right? But I only have 3 questions left, so we should be able to do that. Okay, so let's check this one here. It says, a set of 5,000 scores on a college readiness exam are known to be approximately normally distributed with a mean of 72 and a standard deviation of 6. To the nearest integer value, approximately how many scores are between 63 and 75? All right, so here we go. Here's our distribution. This is not so bad. They tell us, right? Sorry, that's not a very good curve, but I'm doing my best here, right? They're telling us this thing is centered at 72. The standard deviation is 6. And they want to know how many scores approximately are going to be between 63 and 75. So 75 would be like right here. And 63 would be somewhere to the left of 72. So what I'm thinking is, first, we got to figure out what percentage of scores would fall between these two cutoffs. And then we know that there were 5,000 exams, right? So if I find this percentage and then multiply it by 5,000, I should know how many scores were in here, right? So I'm just going to come back to my calculator, right? And I'm going to tell it all the information they gave us about the distribution. So we're going to make our lower cutoff 63. We're going to make our upper cutoff 75. We're going to tell the calculator that the mean is 72 and the standard deviation is 6, right? Second distribution, normal CDF, all right? What did we say? 63 is the lower boundary. 75 is the upper boundary. I got to double check the mean. The mean was 72 and the standard deviation was 6. So now we're going to find out that out of the 5,000 people who took this test, about 62% and change should have scored between a 63 and a 75. So if I just take this whole decimal here, right? Don't round yet. Wait till the end. I'll multiply it by 5,000. And I'm going to round this to the nearest whole number, right? 3,123.27. I'm going to round that down to 3,123. And if I look at my answer choices, there it is to the nearest integer, 3,123. So that's not so bad. And then it says for the data described in problem 5, which score is closest to the 63rd percentile? So now they're not giving me cutoffs and asking me for an area. They gave me an area and they're asking me for a cutoff. That is an inverse norm function. So I'll hit second distribution. Now I'm going to use inverse norm. And now I just have to figure out a few things here, right? They want the 63rd percentile. So the number that I'm looking for is going to cut off the bottom 63% of the distribution from the top 37%. So I'm going to tell the calculator I want the cutoff point for the area to the left, 63% area to the left. All right, I could do this problem in terms of z-scores too, but why make it hard on ourselves, right? They're telling us the mean is 72 and the standard deviation is 6. So I'm saying on a distribution that has a mean of 72 and a standard deviation of 6, what score is going to represent the cutoff for the 63rd percentile? Paste. And that's going to be really close to a 74, right? 73.99. So let's see what our answer choices are. There's 74. So it's got to be that one. Okay. And it looks like I got one more here. All right. It says one of the values in a normal distribution is 43. Its z-score is 1.65. If the mean of the distribution is 40, what is the standard deviation? So this is a little twist, right, on the z-score formula. So remember, the z-score formula is some score minus the mean divided by the standard deviation, right? So I'll use the sample standard deviation symbol here. So if you're just thinking about, some regular algebra here, there are 1, 2, 3, 4 variables. I should be able to give you any 3 of these and ask you to find the other one, okay? So in this case, it looks like they gave us a score. They're saying a value in the normal distribution is 43. So they give us the score, they give us the z-score, and they give us the mean. So they give us this number, and this number. And they ask for the standard deviation. Fine, we can do that. Okay, so let's just plug in. They're telling me a value in the normal distribution is a 43. They're telling us the mean of that distribution was 40. And they're telling us that this score represents 1.65 standard deviations above average. So can I figure out what the standard deviation is? Of course I can, right? I just need to solve for the standard deviation variable down here, okay? So if it was me, right, if you remember your algebra, I mean, this looks like a proportion to me, right? I should be able to put this over 1 and cross multiply. If you don't like looking at it like that, right, I would think, okay, how do I get this variable out of the fraction over here? I'm going to multiply by Sx on both sides. Okay, these will cancel on the right. So I have 1.65 standard deviations is equal to the difference between 43 minus 40. Obviously, 43 minus 40 is 3. So basically what we're saying is being 3 points above average is equivalent to being 1.65 standard deviations above average. So how do I figure out the standard deviation? I'm going to divide both sides by 1.65. Okay. And when I pull up my calculator, 3 divided by 1.65 gives me 1.818. Let's look at our answer choices. And how about 1.82? 1.818 rounds to 1.82. All right. And that's it. So hopefully you guys have a better understanding of z-scores now and percentile ranks and how the area under the normal curve is equivalent to a percentile rank. And hopefully you're familiar with this formula, okay? So I should be able to give you any three of these values and ask you to find the missing one. So make sure you have this equation committed to memory and you're familiar with manipulating, the equation to find any of the missing numbers that I can give you or ask you for if I give you the other three numbers. All right. And that is it for this. So now we're actually through the first 3 chapters. And my next video should be on 2 variable data. I think that's chapter 4 in your textbook. I could be wrong off the top of my head. Maybe it's chapter 3. I would have to go back and check, but no big deal. Get ready for 2 variable analysis next. All right. See you guys next time.